All right, mechanical work. And in this chapter, we also discuss kinetic energy. Okay, if I have an object and I take that object and I so if I take an object and I pull on it, like this, I'll give you an example here. I think you can see that. That'll be our workbench. And I will take an object, like a rectangular mass. This guy right here. And I'm going to pull on this object with a horizontal force. Let's assume it's frictionless surface. And I'm just going to pull on it right now. So I know it's, I mean, we could put, we know, actually there is friction, but you know, friction is in the opposite direction. If it's frictionless, it will accelerate. But if there's a frictionless surface, you know, I can pull it in such a way that it will move at a constant speed, that the frictional force is equal opposite to the force I pull. So we don't have to negate friction. We can put that in, but I want to just focus on the work done by each individual force individually. So the first, let's just think about the applied force. As I pull along at a constant speed, now here I have it put it as horizontal, but just to emphasize the overall definition, general definition of work, I'm going to pull it at an tension force is at an angle relative to the horizontal, right? As I pull along, okay? Now, that is the diagram that I'm going to illustrate here. This diagram is going to illustrate that physical scenario that I was just dramatizing or demonstrating. And yeah, so I can illustrate it thusly. So I have a mass here. And I'm going to tether it with a string, like so. And this is going to be my applied force. So that's F applied. And I'm pulling it, as I said, relative to the horizontal. And I can define an angle theta associated with that horizontal. So nothing fancy. All this is stuff should be pretty good. So that's theta. Okay. Now, sure, I've got two forces on this thing already. I've got the normal force and gravity, which we should be familiar with. So mg is down, okay. Normal force is up. And if I'm assuming it's moving at a constant speed, I definitely have to have a frictional force, opposite direction motion. Otherwise, it would be accelerated, right? Okay. We'll put friction. But right now, and ultimately, we're going to look at the work done by all of these forces as this object moves through a distance delta x. This is x naught, and you can make it 0 if you want. And this is x. So delta x, of course, any delta quantity is always final minus initial. So x is actually x final minus x initial. Okay? So mechanical work is defined as essentially the force, and let's make it tension. Let's go ahead and make it tension just so I have to keep writing F sub L, or F sub AP. So we'll make this just tension, T. So that's our force. Technically,
Dr. Gamble.
yes.
Is that
Yes.
what's that next to delta x is equal to, is that x final minus x initial?
You're cutting out. I couldn't hear you.
Yeah. Next to the delta x, is that equal to x final minus x initial, or is it just x minus x? Yeah.
Here? Yes. X final minus an issue. Is it not clear? Is the screen blurry or something?
Just a little bit.
How's the connection? It's a little blurry. Let me
It's
check. Maybe I didn't.
okay.
Yeah. So it should be all right. Wi-Fi is in. Sometimes I forget to turn the Wi-Fi on and it makes it blurry. That was the case the other day, and I didn't realize it until after class. But yeah, it's good. Yeah, x minus x naught, right? You got that? Jesus?
Yes.
Okay. All right. So mechanical work is defined as the change in is equal to the product of the tension, the magnitude of the tension, times the magnitude of the displace of the path. It's really not a displacement. The terminology is used as path. And we'll talk about that why later. The magnitude of the path times the cosine of the angle between those two things, where the direction of the path is, in the direction of motion, and t is the force. Now, I want to just show you something. So that's the definition. Let's go to some properties. The units is of work so the symbol for work is just capital W. So brackets means units. So the units is just going to be a Newton times a meter because cosine doesn't have any sign. So the unit is a Newton meter. I guess we could break it down a little further, where a Newton, of course, is a kilogram meter per second squared, so times a meter. So that's equal to a kilogram meter squared per second squared. And we have a name for that. That's called a joule. So the joule with symbol capital J is equal to a kilogram meter squared per second squared. So that's the unit of work is joule. In base units, it's kilogram meter squared per second squared. A lot of times people just refer to it as Newton meter. I don't really need it. Units don't have vector symbols. So Newton times a meter. Work is a scalar quantity. And that should give you a hint about another way that we could write this. But I'll say before I write it like that, I'm going to say something else that I'm going to prove here graphically. That only the component of a force in the direction of motion does work on an object. That's important. Property. Oh man, I'm running out of ink here. Well, I should say along the coordinate direction. So it could be in the opposite the motion or in the same, or along. So it could be parallel or anti-parallel. Contributes to the work. Now, work itself doesn't have a direction. It's a scalar quantity. But the work is done by a force, and a force does have direction, as does the motion of the object. So what we're saying is that for a force, only the component of the force in the direction of motion or along the coordinate direction of motion contributes to the work. Now, what I'm saying is, look here, this thing is moving along a horizontal direction. So I might describe it as the x direction. Now, we could be moving in the positive x direction or the negative x direction. In this case, we're moving, if you assume the right is positive, we can superimpose an axis, and that's to the right, okay? So I should have drawn this from the center of mass, but just let me do it here. Because that's normally how we draw forces. So if I was assuming that the forces were acting, from a coordinate system situated like this, I think clearly this thing is moving along the positive x direction. And the tension itself has two components. One is, one direction is horizontal and one direction is vertical. I just got some new pins. Let me take out a different color here. I'm going to use orange. Not orange color. The diversity here. Yeah. And just a little black. So we're going to first go ahead and do this, resolve that tension into the components that it has along the horizontal direction as well as along the vertical direction. Go ahead and do that for me right now. These work. Yeah, I can drop it. Wow. How well you can see that. Pink. There we go. Still here, just trying to see this situation. All right, a little better. So, yeah, a little better. So, yeah, we've got a component there and a component here. So this obviously is going to be equal to t times the cosine of theta, right? And this is t times the sine of theta. Yeah. So the sine of the angle is, well, I guess what you see is that this force, T sine theta, it doesn't contribute to the motion, right? Because the motion is, now it might cause it to go up. We don't know that depending on the amount of tension. I guess, in fact, it would, because we know if the thing is stationary, it's going to cause it, because we know the normal force is equal to mg. So if you add any force to that, it could cause it to actually, no, it's not necessarily true. It could just decrease the normal force, right? It depends on how fast. It doesn't necessarily cause it to lift off the ground. I guess the tension force would have to ultimately be larger than mg for that to happen. Well, what it certainly does is decrease the magnitude of the normal force. But it doesn't contribute to the motion in the horizontal direction. And also, when you put T sine theta is a force itself, right? That's the force in that direction. But technically speaking, T sine theta is 90 degrees relative to the direction of motion. So if I really wanted to look at that force, to work on that force, I would have to multiply T sine theta times the cosine of, times delta x times the cosine of 90, which would give you 0. The cosine of 90 degrees is 0. Point is that since it's only the tension force T cosine theta in the direction of motion that causes it to move in that direction in the first place, then when you calculate the work done by the force in that direction, by tension in that direction, then you can only take in consideration the component of that force that causes it to move along that direction in the first place. So that's what this statement means. In fact, if you looked at the work done by the normal force, let's look at that specifically, or gravity, using this definition, look at what you get. You get the normal force is 90 degrees relative to the direction of motion, so is mg. So if you use those forces, the work done by gravity, for example, is going to be the force of gravity, mg, times delta x, times the cosine of 90 degrees. But the cosine of 90 degrees is 0, so the work done by gravity is equal to 0. There is no work done by gravity. Likewise, the normal force is going to give you 0 work as well. Normal force is equal to, or the work done by the normal force is equal to the magnitude of the normal force times delta x times the cosine of 90 degrees, which again is 0. The work done by the normal force is 0. The frictional force in this case is actually in the opposite direction as it moves through delta x. So the frictional force, the work done by friction, would be equal to the frictional force, or the magnitude thereof, times delta x, times the cosine of 180. But we know the frictional force is equal to mu n. And cosine of 180 is -1. But also n, if you apply the first law, by now you should realize we shouldn't have to do that so much, but it's the first law applies in the horizontal direction. So the normal force equals mg. So for this one, so I could put in, substitute that in for the normal force here. And what we will see is that mu times mg times delta x Well, actually, it's negative, right? Because I'll bring that negative sign out front. So the work done by the frictional force as the mass moves along the path length delta x is going to be equal to minus mu mg delta x. And it's negative. So it takes out some of the energy, right? And that's, yeah, it basically takes, the string is doing positive work, causing the velocity to increase, but it can only do that so much because a constant amount of, or a certain amount, not constant, but the frictional force is taking energy out even as we move along, and the tension force is putting energy into the system and trying to increase the velocity. So the total work done is work and working. Now, net work on the system is the work done by all forces on the system. We can write that. The net work net equals the sum of all work W sub i's is the scalar sum of work done by all external forces on the object. I think I need a felt pen. This is not the best cap. Yeah. I think I got a pointed cap. I should have got a different kind of cap. I do think so. Yeah, possibly. We'll see.
Professor, I have a question.
Yeah.
Why is on your friction, why is cosine 180?
This angle is the angle between the direction of motion and the force. Perhaps I should say. So in fact, I should probably box that in and say that, right? Yeah, I think I need a bigger. And that's also, I should have made that a property somewhere. Let's do it up here. Just do it like that. So that angle theta between the direction of motion and the force. So the direction of motion is positive x, and the direction of the component of work that's doing, the component of the force that's doing work, t cosine theta, is in the same direction. So the angle between them is 0. Over here, the direction of the motion is still in the positive x direction, but the frictional force is in the negative x direction. So the angle between them is 180 degrees. That's where this 180 is coming from. Do you see that?
Yeah.
So cosine of 180 is -1. So,
Okay.
yeah. So if I need some more space, yeah, I do. So I guess I'll come here and I'll say that the total work here, if I wrote a mathematical equation, well, first, I don't think I actually wrote out the work for this. The work for this is just the work for the tension force is going to be, so tension, work due to tension is equal to T times delta X times the cosine of 0. So that work is just T times delta X. So then the total work is the work done by tension plus the work done by friction. So in the end, the total net work on the system would be WT, which is T times delta X plus WF, which is actually minus mu M G times delta X. I guess you could simplify it a little bit. You could say that the total work done on the system in this case by all forces, friction, normal force, gravity, and the tension force would be equal to, factor out the delta X, and then you would have T minus mu mg. So that would be the final and total work done on the system. This would be the answer when I put in the numbers for that. Does that make sense? Any questions about that? Somebody give me some feedback. Does that make sense?
Yes.
Yeah. Let me give you another example before we do a problem or two. I do want to do a problem. See how you work this, but let me illustrate something for you here. It's something called, let me do this. Excuse my junky apartment, might be a little bit messy a little bit, but let me see the floor over there. I'm going to get some dumbbells here, and I'm going to do something called there's a workout routine called the farmer's walk that bodybuilders do in the gym. Okay, can everybody see me? My dumbbells here?
Yeah.
All right, so we'll do a little demonstration, and it's going to be in 3 parts. Oof, Lord. I'm going to pick my dumbbells up. I'm going to walk a couple feet, and then I'm going to put my dumbbells down. So we're going to have 3 parts to this path, or 3 parts to this demonstration. We're going to calculate the work done by me, not gravity, but by me, through each phase. The phase of picking up the dumbbells and moving, walking horizontally, then putting down the dumbbells. Now, I'm going to do this in such a way that whenever the dumbbells move in each portion of the path, the dumbbells are moving at a constant speed. So when I pick them up, I apply just enough force that's equal to the weight, so that they move up at a constant speed, no acceleration. When I walk horizontally, well, the dumbbells are also moving horizontally, but I still have a force on them. My force is still vertical, because if I let them go, they would drop down. So clearly, gravity is mg acting down, and my hand is equal and opposite gravity. So it's the first law, no acceleration in that case as well. My applied force is equal to the weight. And when I set the dumbbells down, I'm going to move down so that I have no acceleration. So even as I move down, once I start, then the force I'm applying is equal and opposite to gravity, and they move down at a constant velocity. Now let's assume that let's just call the distance that I move. In each case, we can make it the same. So I picked it up about 2 feet, moved 2 feet, set it down 2 feet. So we'll call that path in each phase delta x. And actually, you know what? I guess we could, let's just assume that I picked it up a meter. And, you know, we don't have to put numbers in. Let's just say that my path is delta x, same path every time. And the weight, the force I'm applying, let's just call it F. I know it's the weight. I don't know. We can figure out probably what the weight is, but let's just call it F. So, and let's pick somebody to help me with this. So, yeah, Abdul, I want you to determine the work in path 1. Dami, I want you to determine the work in path 2. And Shura, I want you to tell me the work in path 3. And I want you to give me the amount of work in terms of F and delta X. Okay. So Abdul, you're up first. This is path 1. And I'm going to do it once, then you don't have to respond. Let's do it once or twice, and then just have you look at me, and I'll tell you what path is what, just so you know. And then we'll come back and see if we can get the answers from everybody. Okay, so this is path 1. I'm applying force F, and I'm moving the dumbbells through distance delta X. So that's path 1. I did work, so just think about how much work was done. Abdul. Now, I'm going to move through path 2, delta X. Find the force. Now I'm going to set down the dumbbells at a constant velocity, applying a constant force, and they move through delta X. Okay? So again, pick up the dumbbells, path 1. Dumbbells are moving up. Think of the motion, the direction of motion relative to the direction of the force. I walk through delta X instead of the direction of motion relative to the direction of the force applied. And I set the dumbbells down. Path 3. Consider the direction of motion relative to the direction of the force applied. And in each case, the path they moved is delta X, that's a number, and the amount of force applied was F, that is a number. Okay, Abdul, how much work was done during the first path given the definition of work that I've described earlier?
You said in terms of what?
In terms of the given quantities. What are the given quantities?
Okay.
You know what I mean by given quantities? So what are the given quantities? Start with that.
Gravity, mg. And,
Yes. What else?
And what you call it? Time, t.
I don't think I told you how long it took me to do those things. I didn't give you time. Yes, Dami, the displacement, that's what we call delta x. So let me write on the board. Delta x. So in that experiment, we had 3 paths. We had the path. So basically, in each path, I told you that I moved the dumbbells through delta x. So that's given. That's a value. It's a number. And I told you that I applied a force, and the force I applied was F. Now, you also have some implicit information there. So I thought that's where you're going with that. Since I picked the object up at a constant velocity, I know implicitly that the mass is m, and its weight is g. So the weight of the object is mg. So that's implicit. And so if I pick the object up at a constant speed, then basically in each path, F is equal to mg. It's equal to mg when I pick it up. It's equal to mg when I'm moving along horizontally. And F is equal to mg when I set it down, because I said that I was not accelerating the object at every point. So that should be, yeah. Yeah, I don't really know how to draw it. Like if in path 1, here's the ground, here's the dumbbells moved from the ground to some height, delta x. So delta x was that height, and they moved up to this height, right? As they're moving, it's moving along a constant speed. So anywhere along that path, F is up and mg was down. And I picked them up at a constant speed. So F was equal to mg as I moved it up. For path 2, right, the objects move through delta x. Like if you look at the side view, the dumbbells were here, and they moved along to here. And at every point, F is up, the force I'm holding it, mg is down. Now in this path, the object was moving up, right? So you have to also consider the direction. Delta x here is just the magnitude, but it has a direction relative to F. And over here, for path 3, basically the same picture as this, it's just the object is moving down, right? There's the ground. The dumbbell was here initially, then it was on the ground. It moved this direction, right? So the distance it moved was delta x. But still, at any point, F is up on the object and mg was down. So what I'm asking you to do is to use what we just talked about here to calculate the work through the work in every path, every part. I'm gonna go ahead and erase this. So what I'm asking you to do, or I'll do, is to tell me, or each of you, I want you to calculate the work done along path 1, the work done along path 2, the work done along path 3, and then calculate the total work that I did over the overall path 1, 2, and 3 together. So right now, Abdul, you're up. What is the work done in terms of given quantities for path 1? That's the question that you're being asked. So now do you understand the question? So I need some response, folks. We're talking, we're having a discussion. It's one thing not to be able to see you, but when I ask you something, you don't talk. Like the question is, do you understand what you're being asked? Yes or no?
You mean like do the equation?
I mean, do you understand what I'm asking you to do?
No, honestly, I don't.
Okay, all right, fair enough. Does anyone understand what I'm asking? Uh, sorry. You know, it would help if you had a statement like it would help. You know, there's a lot of people talking like you could turn on your cameras and just tell me what if you have or turn on your microphone. It's kind of hard to go back and forth when a lot of people ask. You know, it's okay sometimes. Seven passing with the force be greater than the weight because that force is being used to pick it up. That's a good question, Dami. So good. Let me answer that question first. So it would have to be in the first instant, right? Like I would have to apply, you know, maybe you might think of it like that, right? That it would have to be a little bit greater. But once I started moving, then I can move it at a constant speed. Like if the force that I'm using is always greater than the weight, then the object is going to accelerate. It's going to be the second law, right? But when I pick it up at a constant speed, sure, maybe initially in some microsecond that it took me to start the motion, but once I start the motion, it's moving up at a constant speed. So that was the point, that everywhere along the path, F is equal to mg. Does that make sense?
Yes.
Okay, good. So that answers that question. I don't know. Any other question? Or what would be a time to solve the work in each path in terms of quantities given? I would agree with Dami to stuff. What did Dami say? What do you agree with?
Hello.
Hey,
Hi. I thought on his first statement where the force was greater than the weight, I thought it was I agreed with it at first. So
that the force, yeah, but do you understand now that when I say I'm picking it up at a constant, uh, it's moving up at a constant velocity, then that's not the case. And do you
yeah.
understand it? Yeah. So yeah, maybe initially I had to kind of overcome the weight a little bit to get it moving.
Yeah.
But once it's moving, yeah. It's kind of like an elevator, right? We looked at the elevator problem. Initially, when you're on the elevator starts moving up and you are accelerating because your apparent weight increases. We did that problem. But after that only happens in a short amount of time if it's a huge building. After a while, you go up at a constant speed. So when you look at the scale, your weight is back to what it normally is, which means that the normal force on you and the weight of gravity on you is the same. You're moving up at a constant speed. And then when you slow down, then you're lighter, right? Because it feels like the gravity is greater than the force on you up, which is why you're decelerating to zero. So it's the same scenario, but when you pick something up, the amount of time that you're accelerating is happening in a very small instant of time, like, you know, maybe milliseconds. And so you pick it up and then you're at a constant. Can you see? Oh, you can't really see here. Sorry, this was out of here. I'm using this thing when it's out of the frame of view. Ouch. So yeah. So I initially pick it up, you know, maybe some millisecond is accelerating, but then it's moving up at a constant speed. And for some millisecond, it slows down. Clearly, it's accelerating, and so the forces are not the same. But that's only in the instant, you know, basically that I stop. Some very short amount of time. Right? Same thing going down. Accelerate, but then constant speed. Now, yeah, you know, I'm controlling the experiment. Maybe I pick it up and it is, I don't know, you know, like, but I'm doing it in a controlled fashion. That's why I did it very slowly and deliberately. So like it's almost like an elevator arm, right? Or like a robotic arm, you know, like if you do the robot, you know how they do those jerky moves, right? It starts moving, then it moves at a constant speed, then it stops. That's what makes people kind of do that kind of motion. It looks like that, right? Because they're starting and they're kind of, I mean, I think you get what I'm trying to say, yeah. So, but it's a great question. It's a great question. So that's the kind of thing you need to think through, because I'm not really giving you any numbers, and you don't really need any numbers in order to, in fact, numbers can kind of cloud the physics here. that what basically I'm giving you numbers in terms of symbols. F is a number. That's the amount of force I'm applying. And yeah, implicitly, that means that it's got to be equal to the weight as I pick it up, right? Delta X is a number, but it's delta X. You don't need the number. So from that, use that to decide how much work in terms of these given quantities am I doing in terms of F, in terms of delta X, basically, and any other applied constants. Okay?
So you want us to, like, for example, create a equation, right? Like forward mg times cos theta sine theta. Is that was the
Yeah.
question?
Yes, but yeah, that is the question, but it's not really about equations. I mean, the equations represent physical quantities. And in this case, the physical quantity that I want you to determine is the work. And the equation that defines the work is the equation that I just erased. Work is equal to a magnitude of a force times a magnitude of a path length times the cosine of the angle between them. Does that make sense?
Because Professor, in this one, because the cosine, like let's say path one, right? Path one, you're going straight up. Yeah.
Yes. Yes.
So there's no angle there, right? So there's like it's
Yeah, that's what I was gonna say. There's no angle there, so I don't know
right,
if
so
that
would
equation.
one because it's
Hey,
like
good question. Very good question. I would disagree with you. There is always an angle between things. Always.
Okay.
You can always define an angle. Say again?
I was saying, okay, there's like background noise.
Oh. So you can always define an angle relative to something. So when you say there's no angle, what do you mean by that? I don't get it.
Like, for example, when it's going straight up, right? Would cosine in that, let's say theta in that one, would theta be like 0? Because then cosine would be just 1, right? So it wouldn't affect the problem. Would that make sense? Or...
Well, it does affect it. It's 1, but it is what it is. Dami, do you agree with that? You said it was no angle. It was no angle either.
I mean, if it's going in the upward direction, the angle either should be 0 or 90. And if it's 90, that means the work done will be 0.
Why is the angle? How is the angle going to be 90?
If x, if you're looking at it in the Cartesian plane, that x is the level of the floor, and y is the upward direction that you're carrying, that you're lifting the weight.
Okay, let's back up a minute. So I get what you're saying, and if that were the case, it would be true. But you could call it's just a path length. I have to use something. I like to use the delta as opposed to delta something as opposed to d, or like it's a path length. I'm not necessarily saying that delta x is along the x-axis or the y-axis. It's just a path length. So in the case of the first, you see, I called it delta x, but it's vertical, right? So I'm not saying that delta x is necessarily in the horizontal direction. It's just a path length, the path length that the object is moving. And in this case, that happens to be vertical.
Okay.
Do you get that?
Yeah.
Yeah, so this is not necessarily a coordinate.
It's just a displacement.
Yeah, it's just and be careful about the term displacement. I know I have used that in the past, and you are correct to see that as but if you look in your book, any physics book, it's not gonna, whenever it defines work, it does not call delta x displacement. It calls it path difference. And there's a deliberate reason why it does that. That's why I'm using that language. So whenever you're talking about work, I'm going to encourage you not to call delta x a displacement. That can get you into trouble, which we'll talk about a little bit later once we can get a basic understanding of how to use this formula and how it describes work. But that's a little bit more intermediate subject to talk about. Right now, we're still trying to get a hold on what this is. So for now, let's just call it path length. Okay?
Yeah.
Okay. So Abdul, you had a question, and you seem to be having some insight coming along. So I want to come back to, do you have a question you need to ask me right now about anything?
Yeah, I
clarify?
was thinking the same that Roy was thinking about the 90-degree thing, and Dami was telling. First, I'm confused. Like, how'd you get cos 0?
Okay. The definition of work, and I've already erased it, is that angle theta is the angle between the direction of the force and the direction of motion. So Abdul, come back to path 1. What is the direction of the force that I'm applying on the object? That I'm applying, not gravity, me.
Upward.
Upward. What is the direction of motion of the object?
Downward.
No, I picked the thing up.
Oh, sorry. Yeah. Sorry.
That's all right. It's all right. It's all good. So, but I want you to answer, what is the direction of, what is the direction of motion?
Upward.
Upward. So what is the angle between the two? They both have a direction, so there's got to be an angle between those two vectors, because remember, they're vectors. F is pointing up, and the direction of motion is up. That could be, you could represent that as a vector. If they're pointing up, what is the angle between the two vectors? They're parallel. So what is the angle between them? What does parallel mean?
Parallel.
Someone just answered. Can you
0.
see the 0? Dami, yeah. Yeah, and I know it's, we probably don't think of it that way, but we can. That's what I mean, that you can always define an angle between objects. Even if it's 0, it's still an angle. It's not an angle. It is an angle, and the angle is 0. Right? That's what direction means. And it's important for this problem because this whole thing is based on that. Right? Like it's important. So we can now begin to think in that. We have to kind of expand our mind a little bit when we start to deal with work.
Professor,
yeah.
I have a question.
Yes.
So work is you said it was a scalar, right?
Yes.
Regarding that, is it? I'm thinking of it now, and I feel like this is kind of a dumb question, but can we ever get a negative work?
Yes, we can. Yes, we can.
Like, for example, like in W3, right? So how it's going down. So the motion would be downwards, right?
Yes.
But then the force that we're applying to it, is it upwards? It's an upward force because we're trying not to. Okay, so if let's say, like, in an example, right, that we get a total work of like negative, what does that mean physics wise? Like,
well, that's what I'm about to ask you. That's why I'm doing this problem. Hold that thought. That's good. Good question. Hold that thought for a minute. Hold that thought. And when we get to that, then we're going to revisit that question. In fact, that's actually what this last part is all about. So let's hold that thought for a minute. And let's just go through each step. So back to Abdul. So Abdul, sounds like you've made had some enlightenment here and understand, kind of getting on track about what we're doing here. So again, direction of the force is up, the direction of motion is up, the angle between them is 0. So how much work is done on the object when I pick it up through a distance of delta x?
Much work.
Okay, you're applying this formula. So apply the formula to this thing. Put in the values. What's the value of the force? I mean, do you understand what I mean by apply this formula?
Yeah, I did. I just don't get it. Like, why do we get cos 0?
What, say again?
I just don't get it. Why are you using cos 0?
I didn't quite. Could you say that one more time?
Yeah, I get the formula. I just don't get why you're using cos 0.
You don't get why cos 0. Why that?
Yeah, well, cos 0 is there.
Sir, I have a similar question to that.
Yes.
You said the angle in between was 0, but why is
Yes.
why did you put cosine of 90 at the top right corner work of G? You have cosine of 90 in between mg and delta x.
You know
That's a
this is
different
a
question. That's a
You
different
know that's a different.
Yeah.
You know that's a different problem, right?
Yeah.
Because in that case, that was the force of. I mean, it's a different problem. Like the object was moving horizontally in that case, and gravity was acting straight down. So the direction of the motion was horizontal, and gravity was down. So the angle between them is 90 degrees.
Okay. I got it now.
Okay.
Yeah.
Okay, Abdul, I'm back to you. You don't. So you just walked through it. You said that F was up and the direction of motion was up, and so you're telling me now you don't understand why the angle is 0.
No. Why are we using cos?
Why are you using cosine?
Yeah.
Okay, so cosine of theta, not cosine of 0. I mean, the
Yeah.
formula is cosine of theta. Okay, because that's the Okay, that's a great question. Great question. Because that's the definition of work. We define it that way. Mechanical work is defined as the direction of the motion, the magnitude of the force times the direction along which the object is moving times the cosine of the angle between that force and the direction of motion. It is defined that way. That is the definition of mechanical work.
So would it like the direction would affect like if it's going horizontal or vertical is still gonna be cosine?
That's right. But it's the relative direction. It's not the direction. This angle is not the angle of direction. It's the angle between the force and the direction of motion.
Got it.
Okay?
Yeah.
Yes. So 3 equal signs means a definition. Okay? Now, can you apply that definition of work to this specific problem of along path 1? Which means that you have to take this definition, you have to look at path 1, put in the value of the force of that path, the value of delta of the path length for that path, and the angle between them, and then do the algebra in terms of that problem in the parameters that I gave you for that problem. Can you do that right now?
Yeah, like force times delta x times mg cos 0. Is that?
Yeah, so tell me what to write. What is it for path 1?
Force.
Okay, F, yes.
Delta x.
Okay, F times delta x, yes.
Mg.
Okay.
And cos 0.
And cos 0. Okay. So you have both F and mg. Why did you do that?
Because as you're applying the force of gravity is acting on the object as well, and they're equal.
Okay. Now, that's a good point. Those are 2 different forces, though.
Yeah.
So, and they're not acting along the same direction.
No.
What I specifically said, but good, very good. That you're kind of on the right track. If you were to look at both forces, you wouldn't quite do it like this, but I do get what you're trying to do. But when I started this problem, I asked you to determine the work that I'm doing on the object, not gravity. I specifically said that. You remember?
Yeah, got it.
So let's go back and do that again, but only calculate the work that I'm doing on the object, provided that I'm picking up the object at a constant speed. So go ahead.
It's going to be force times delta x cos 0.
Force times delta x cosine of 0. And what's the cosine of 0?
0. Oh, no. Cosine of 0. Cos 0, sine, cosine. 1. 1, yeah.
1. So this will reduce to f times delta x. Very good. There's one other thing we can do, and this might be a little bit confusing, but we'll clear it up. I actually can write what the force is. I know what the force is in terms of the mass of the weight of the object. What is that force equal to?
Can you repeat
Give
it
you a
again?
hint. Yes,
Can you repeat
I
it?
can go one step further. I know what the force is in terms of the weight of the object.
Equals to
So
mg.
it equals to mg. Dami's correct. Why? Because we did those problems. I'm picking it up at a constant speed. So if I apply the first law, F equals mg. I did it right here, right? So
Yeah.
I could go one step further and I could say that the work done by me as I pick the thing up at a constant speed is equal to positive mg delta x. So good, Dami. Good for you. So does everyone see that? The work that I do for path one is equal to mg delta x.
Why
Any
is
questions about
mg positive?
It's just a magnitude. Mg is mg. Mg is a magnitude. It's not positive or negative. Is that unclear for you? Let's go back and do it again. So look, let's do the first law. If you have an object, if I'm picking up an object with a force at a constant rate, that means that the velocity is constant and the acceleration is 0 in the y direction if I pick it up. So at any point, I have the force that I'm applying on the object and I have mg down. So goes back to the last couple chapters. What law applies to that as I move it up through? And let's even give it some. Let's say I went from the ground, so I'm picking it up through a distance delta x to here. Okay. What force law applies? The first law or the second law? Jesus.
It's the first law.
It's the first law. So let's apply it. Net force equals 0. All right. Why is it 0? Because it's not accelerating. Okay. What forces are on the object? So maybe this is where you're getting the minus sign. I could say T up and down is, and force, tension up or whatever is positive and gravity is negative. Okay, fine. So T minus mg equals 0. But in the end, T just equals mg. So we're looking at the magnitude. Like weight it has a direction, sure, but that's relative to a coordinate system. But it doesn't have an inherent direction. It's just mg. It's just a magnitude.
Okay, I see it.
So once we calculated what that magnitude is, we put it in. And you got to be careful. It's a good question you're asking, because we've already incorporated this minus sign. We've already incorporated that whenever we look at the cosine of the angle. And that's something that can happen as we move forward. You got to be careful about it. Either you take in the direction, because remember, this is the magnitude of f times the magnitude of delta x. So we're just dealing with the magnitudes of these things here. I've already figured out what their signs are. I've done that when I'm talking about the relative directions. Let me do something else that you all may not realize. And I didn't do it initially. Maybe I should have. I don't know. But I'd like you to think about it first. Something like this you should be familiar with in terms of a mathematical equation. You have a vector quantity times a vector quantity times the cosine of the angle between them. Doesn't that look familiar? What type of mathematical quantity is that? Let me give you a hint. What type of mathematical product is that? You can multiply vector quantities one of two ways. This is one of those ways. I thought everybody had calculus already. What ways can you multiply two vector quantities? Nobody? Easier?
I don't know if it's right or not. Maybe the length. I'm not sure.
The length?
Maybe. I'm not sure. It's just a guess.
Cross product?
Well, cross product is one. And what's the other? Good deal.
Dot?
Yeah, cross product and dot product. What are those definitions? What's the definition of a dot product? If you have a product of, just choose some arbitrary vectors A and B. If you have a dot product, the way you write it is you have vector A dot vector B. What does that equal? What is the definition of that?
Still scalar? Becomes a scalar.
I mean, it will give you a scalar quantity, yeah, but it has a definition in terms of the magnitudes of those vectors. What is the definition of it? How do you compute a dot product if you have a vector A and a vector B?
Do you multiply them?
Give me a complete sentence. Yes, of course you multiply them as a product. But how?
Is it a vector perpendicular?
I take like little things people like say or do, and then just like.
No.
Sure. You remember? Yes, no. Let's see, you think, or did you somebody write some? What about you, David Edwards? Do you remember what the definition of a dot product is? No, sure, I couldn't hear you. No. Still can't hear you. I see your microphone is off, but I can't hear you. It does say on, yeah, but I can't hear you. It looks like it's on from here, but I still can't hear you.
Professor, would it be for the dot product? Would it be the like I'm trying to recall it, right? And I know that it's something where it's like you put the where you put the like the head and tail together, right? But would it be like, for example, you're adding the x direction of A and the x direction of B, and then something like that?
Okay, no, folks, and sure, no, I mean, sure, I mean, kind of, but not quite. Like that, no, that's vector addition, Roy.
Okay.
That's like, you know, that's like we're multiplying it. That's vector addition, head to tail method. That's like parallelogram method.
Okay.
That's but you know, it's cool. It's all right. I mean, it's a lot of times it's dramatized in that way. But no, let me just tell you.
Okay.
The definition of a dot product is that it's the magnitude of one vector. So I'm using absolute value times the magnitude of another vector times the cosine of the angle between those two vectors.
Oh, okay, yeah, and that's the work formula. So, yeah.
Yeah. So that's just a mathematical definition of dot product. But what I'm trying to show you is that since this is the definition of work, you can write it in terms of a dot product. That work is equal to F dot delta X. So that should help you a little bit if you understand, you know, kind of what parameters are associated with dot product. In here, we probably need to review it. So remember I told you like dot and cross product. And cross product is the other one. Let's see if we can write that out. Cross product. With A cross B. Now that's a little bit harder to represent. Now, actually, there is a graphical representation of this. Let's do dot product first. It's the projection of one vector onto another. So if you have a vector, that's the geometric interpretation. So if I have a vector like A here, and some vector B like so, let's use a different color. What you're actually doing is finding projection of one vector onto the direction of the other vector. So let's say that you have a vector A, right? And the angle between them is theta. So this is the angle between them, theta. Well, what I'm doing, let's drop a perpendicular. I can drop a perpendicular of, oh, sorry. So that's B. I'm going to drop a perpendicular of A onto B, and it could be one on the other. I could do either one relative to the other. But if I do that, then there's a projection of A onto B, which would look something like that, right? Well, but I also have a perpendicular component of A, which is this guy right here. I mean, I could project it over here just to kind of clean it up a little bit. Well, what is this vector and what is that vector? This vector here is A times the cosine of B. And this vector here, sorry, of theta. And this vector here is A times the sine of theta. So it's the cosine of the angle that's the projection and along the same direction as B. So you could call this like an A parallel, for example, A parallel to B, and this could be like an A, the component of A perpendicular to B. So when you take a dot product, what you're doing is picking out the component of one vector that is parallel to the other vector. In fact, you can see it in the definition. This is A cosine theta, which is A parallel. So another way to write a dot product is that it's equal to A parallel times B. But it's really all relative because I could have done it relative to A. In other words, I could have extended A out like this and then projected B onto A like that, which would give me a different right triangle. So I would have B projecting onto A, and then my B perpendicular, I guess it would have been something like, it has got to be 90 degrees to A, so it would have been something like that. Where this is B sine theta. You have to work it out to see that. And this thing here, actually it goes the other direction, wouldn't it? No, it's this one. And then this thing here is B cosine theta. In which case, I could have looked at it like this, and so you could just as easily write it as A times B parallel. It's all relative. So that's the kind of a review of dot product. But what I would suggest for you is that you now go back to chapter 1 and go to the section on, I'm not going to really assign, or maybe I could assign something, I don't know. But I would go back there and review it now. This is the time to go back and review that. Because remember, I told you that I don't really like to do math arbitrarily. I like to do it in turn. And most of that chapter was a math chapter. I like to do it in the context of when we get to that information. Well, we're there now for dot product, and I as well go ahead and review cross product as well. So I would go back and maybe read through that and do some of those exercises there. And you can do adaptive practice for that. I won't necessarily assign it, at least not right now. But the adaptive practice problems would, would give you some stuff to work out with dot product and cross product. In the interest of time, I'm not going to do cross product right now because we won't get to cross product until we get to torque. But I want to keep this lecture moving because we're still doing work. But so now this is an introduction of dot product. So go ahead and review that in chapter 1. And that's kind of the extent of what I would talk about in class. I know it's kind of messy, but whatever. But yeah, cross product is a little bit more complex. Cross product involves, with a cross product, you get a vector quantity as opposed to a scalar, and the direction is perpendicular to both. Go ahead and review it. You review that now. So when we get to torque, you might recognize a little bit quicker than you recognize this. But everything that you guys were saying was right, like it's a scalar. I had said it earlier, but now you see why, right? Because we define it that way. So you can see now this makes sense. The dot product between two vectors gives you a scalar. Abdul, you're asking me why I talked about the cosine of the angle, because I didn't come from a mathematical point of view, right? I could have written this thing down from the beginning, but you see your book won't either. And the reason is because it's not really about the math. The math just happens to be a tool that describes the way we define. It's interesting how it works out coincidentally like that. The dot product happens to be a mathematical tool that works very well for us to use. But it's not the reason we define it this way. The reason we define it this way is because of the physical things I was trying to point out. And it just so happens that the dot product is something that describes that perfectly. So it's really the other way around, which is why I didn't start with dot product and why the book didn't either. Okay, remember this is a physics class, not a math class. And so we're kind of focusing on the physics for that reason. All right. Any questions before I proceed? Any questions about this?
No, that's fine. Thank you.
Okay, good.
I have a question, Professor.
Yes, Roy, go. Mm-hmm.
Going back to the path of so you know how in the first one the degree was 0, the theta was 0, and then it moves to 90.
Well, hold on, back up. When does it move to 90?
Is it 90 in path 2? Because the force is still up, but the motion is to the right?
Yes. It's in path. We hadn't gotten to path 2 yet, but you're right. It is 90 in path 2. That's right.
Okay. So in the other one, path 3, how it's going down, right?
Yes.
It's 180. If let's say that the path, right? Let's say you pick it back up again, and then we move the other way, right? Towards the left. Would it be 90 in? It would still be 90 that way. So my question, right, would be, do we ever have a cosine of theta where it's above 180? If that makes sense,
That's a good question, and that's a very good question. And let me illustrate that with an example.
Okay.
The example I started with. It's a very good question, dude. Very good question. All right. Let's say that, I guess I could do it like this. So right now, this is 0. I'm pulling it. It's going horizontal.
Yeah.
So 0 to 90. So anywhere along 90, what direction does it move? To your right or to your left? Anywhere between 0 and 90.
Moving towards the right.
Yes, right. Now, even when I'm very, up to 9, it's still to the right.
Yeah.
But what happens when I'm 90 degrees? When I'm pulling, is it going to move to the right?
No, it would move upwards.
If anything, if I overcame the weight, it would move upward. But it's definitely not moving to the right. You're right. Now, let's say that I do what you just asked. I go over 90 degrees and I pull. What direction does it move?
It moves towards the left.
Towards the left. That's right. So the answer to your question is technically no, because what is the direction between the angle? The direction between, it's an acute angle, right? Because now it's moving in the opposite direction, and the angle between the direction of motion and the angle between the thing is less than 90 degrees. Awesome. Okay. That's actually one of the characteristics. Good. Yeah. So I didn't write it as a characteristic because I didn't want to get there yet. You can see there's some kind of subtlety in this. If I tell you everything initially, you don't know what I'm talking. Heck, you didn't hardly know what I was talking about just when I wrote down the definition. So
Yeah.
you have to do something like this and go through it before you start to realize the implications.
Okay.
So
okay.
that said, one of the huge implications is that work has a minimum and a maximum based on this definition. The minimum work is going to be 0. And that's going to happen when theta is 90 degrees.
Uh-huh.
The maximum work is going to be F times delta X. And that happens, I don't think it was Roy or Jesus, someone said, when cosine of 0 is 1. And it's not that it doesn't contribute, it's that it's allowing the total, the force to get a maximum work out of its effort.
Mhm.
So in fact, when you have anything less than 0 degrees, the total amount of work decreases because cosine goes from a maximum when the angle is 0 and the cosine is 1 to a minimum when the angle is 90 and the cosine of 90 is 0.
Okay.
Yeah. And the way that I write that, summarize that, is the following. I'm going to leave that up because we're still doing those problems. Good. That this is just a little chart to remember, right? Remember it by. Right. So we can say that we'll call these conditions, I don't know, conditions. And then theta, and then the work. So condition 1, theta is equal to or no, equal to or less than, no, it was 0. Yeah, so this is theta. Theta is, I guess I need a larger thing. Sorry. Okay. I did that. So conditions 1, 2, and 3. Theta is going to be greater than or equal to 0 and less than 90 degrees. So when that's the case, you get a max work is going to be positive, right? And, I guess the magnitude of it would be, I don't know, like, so, I don't know, let me see, we call it, this is theta, and this is, I don't want to say polarity because polarity implies a direction. Yeah, I don't know. Just say either positive work or negative, because it does, even though it doesn't have a direction, you can still have positive and negative work. It has a specific meaning, and this is magnitude. So in this case, if we're talking about F and delta X, then positive, actually, let me just make it sound positive, and the work would be basically the magnitude would be F delta X cosine of theta. You have to put all those values in. if the angle is 90 degrees, then that's trivial, and the work is, there's not positive or negative, and the work is zero because you got cosine of zero. If the angle theta is you know what? I think I might have misled you a little bit. That was for this particular scenario here, where we talked about the angle being for that scenario. That's only one situation. You can have a situation where the angle is between 0 and 80. And that was for the frictional force. That was the first thing I did, right? Like, let's go back to this example. The tension force is changing its direction, but frictional force is inherently always opposite the direction of motion. Like, think about this, Roy. So I'm putting it to the right. The tension force is making it go to the right, but frictional force is opposite the direction of motion.
It's towards the left, yeah.
Yeah. So the angle between the direction of friction and the direction of motion is 180 degrees.
Yeah.
So that's a scenario where you could have something greater than 90 degrees.
Yeah, but
and so
regarding that, my original question was, can you have something over 180 degrees? It wouldn't be the case, right? Because 180 is the opposite direction of the thing that's moving. So like the friction versus that way, like you can't have a theta that's over 180, right?
Yeah, so in that case, it's like it kind of goes back to the scenario that I showed with 90. Yeah, I think it's if the direction of motion would change, for example, or something. You know what I mean? Like, I guess it wouldn't be 180 because in this case, it flipped immediately and was 180. So yeah, I guess the answer is no, right? Because let's look at friction in that scenario I gave. So here, the angle of tension is horizontal, friction is 180. Tension is some other angle, friction 180. Every place, even though the tension force is changing its component, the friction is 180. When I get to 90 degrees, friction is zero because it's not moving. But then as soon as I flip over, friction is now in the opposite direction. So friction doesn't really, it goes from 180 and flips around the other direction. Now, relative to the motion, is still 180. So yeah, that would be a correct assessment. It doesn't really get over 180 is a maximum, I guess, in that case.
Yeah.
Professor?
Yes.
Question. Going off the example you just gave, so if the tension is, if you're calculating the work done by tension, it will be the angle from the floor to the angle from the direction of motion to the force applied.
Yes.
So if we're calculating in a specific direction by tension, if we want to calculate the work done by friction, that means the angle will be over 90. In that scenario you gave.
In that scenario, the angle for friction is always 180 in every case.
Okay.
Do you see that?
Not exactly, but
okay, let me show you again. So I said it real fast, but it doesn't matter what this is doing because the direction of motion is always to the right. If the direction of motion is always to the right, frictional force is always directly to the left.
Direction. Oh yeah.
Yeah, and in every case. So the angle is 180 between friction and the direction of motion, no matter what this is doing.
Okay.
And when I get to 90 degrees, friction is zero because it's not moving horizontally. When I flip over 90 degrees, now the tension is making the thing move in the opposite direction, and the frictional force flips 180 degrees and is going in the opposite direction. So relative to the direction of motion, friction is still 180. You see that? It's not, So the frictional force, the angle is always going to be 180. It doesn't matter.
And another question, why is work a scalar quantity if both force and the delta x are vector quantities? Or is it solely because it's the dot product of The two vectors.
Yes, simple answer. That's right. That is right. That is right. And that's what I wanted to show here. That's why I need to write as a, as a dot product. That's one reason to justify why it's a scalar quantity. That's right.
Professor, I have another question.
Yes.
So what if you're putting the mass upward? Oh, never mind. I got it. Never mind. Sorry about that.
Okay.
Yeah.
All right. Let me finish this little thing here out. So yeah, so now when the angle is between 90 and 180, then the work is going to be negative. Right? So the way you write that is 90 less than theta is less than or equal to 180. And that's basically, I guess you could have some other force on it. I mean, it's not necessary. I mean, who knows what? I don't know. Like maybe you've got two tension forces or something, like it's possible, right? Say that I've got a tension force here and a tension force here, like something like tug a rope or something, right? But I'm pulling up. So this, like I got another string attached and it's pointing like that and both are pulling. Well, now this has an angle relative to the direction of that might be a scenario, Roy, because the angle for this guy would be something that is less than 180, right? But greater than 90, but less than 180, right? As this pulls along. It's all the net forces, right? So, I mean, you just have to work it out. Like you just figure out what the angle is relative direction of motion, and you just calculate, right? And you don't have to worry about a vector analysis because once you calculate that work, then it becomes a scalar quantity. And to get the total work, you just add them all up, regardless of what their signs or anything. But for this situation, you're going to get a negative work if the angle is between 90 and 180. And it will be negative F delta. Well, I guess the magnitude would still be F delta X, cosine of that angle. Now, the final thing is whenever the angle is 0, then you get the maximum work out. And that's, work would be positive, and the maximum would just be F times delta X, because cosine of 0 would be 1. So these are all the kind of general scenarios you would have with that chart. Now, what we're going to see in the next section of this chapter is that there is, even though it's a scalar quantity, you can have positive and negative work, but it doesn't mean direction. What it means is internal energy of the system. You know that when you apply heat to something, you can heat it up, right? You put energy into it. That's giving it energy. Well, that's not the only way to give energy something. You can give something mechanical energy. Let's take a look here. I'm going to do positive work on this thing by picking this object up. I pick it up, and now now I know we haven't defined potential energy, but just intuitively, you know that it doesn't really have, well, let's just deal with friction right now. Friction. When I apply a force on something, I can put energy in the energy of motion, and I can cause it to speed up. Like when you're at a stoplight, you press the accelerator, you apply force to the car, and it speeds up. It changes its velocity. We will define something called kinetic energy, so it has energy of motion. Now, the frictional force, so that's positive energy. You're putting energy into the system, or energy is being converted from the gas to mechanical energies. That's heat and combustion, and it's changing form into kinetic energy in the car. So you cause the car to have kinetic energy. You transform chemical energy from the gas in the combustion process, and it created, it basically put positive kinetic energy into the car. Now, the frictional force, as we just said, is negative. Now, if you take your foot off the accelerator, what happens to the kinetic energy of the car? David Edwards, are you there? You haven't said anything all class period. Called you earlier. Are you there now? Okay. What is happening to the kinetic energy of the car when you take your foot off the accelerator? What does friction do? There's a lot of background noise. I can't really hear you. Try again, or
It don't grow and grow.
yeah, it causes the car to slow down. That's right. That's right. Is that a radio on or something?
And
It can hear you. It can hear you a little bit better if you turn it down or turn it off. If you can, maybe you can. I don't know. Maybe you're in a place where you can't do that. But I think I heard you say it slows the car down. Yeah. And if that's true, then yeah, because it's taking kinetic energy out of the car, right? So that's what negative energy does. It takes energy out of the car. So positive energy means you're putting mechanical energy into something. Positive work means you're putting mechanical energy into something. It can have several forms that we'll talk about, kinetic or potential. Negative work means you're taking energy out of the system, mechanical energy, that is. So that's what it means. Not a direction. There's no direction. It's just, just energy in or energy out. So positive means energy goes into the system. Negative means energy comes out of the system. Mechanical energy, that is. Because there's other kinds of energy. All right. I still want to finish this thing before we get on our break. I didn't think this example is going to take all this time. Let's finish this, though, while we're on that roll. So let's come back to here. Abdul established that the work done in part 1 is mg delta x. Everybody got that? Now, I forget who I had asked to do it. Who was doing part 2? I know, Roy, you've already talked about it a little bit, but let's just stay consistent with how I chose people. Was it, who was supposed to do 2? Sure. All right. Sure, you're up. Calculate the work done in step 2 and go through the process here. Tell me. Go through every step. No, it's not the same. Go through every step, sure. I've got to do F delta X cos theta. So every place, tell me what each value of the quantity is. What's F? Yes, F is equal to mg. So let's do it like this first. So F delta X cos theta, we know that at least that's what. So F is equal to mg, that's right. What is delta X? Oh, we have displacement. So cosine of 90. Yeah, sure. Yeah. So delta X, yeah. And then you have the cosine of 90. That's right. So what is the cosine of 90? Yeah. So how much is 0? So how much work is done then? 0. Wonderful. So it's not the same. The work done in that step is 0. Now let me pause here for a minute. This is something called the farmer's walk. You ever see those bodybuilders? They pick big dumbbells up, right? And then they walk. That's where I'm getting this from. And they walk all over the gym. That's an exercise. It's called the farmer's walk. That's one way to call it. And that's at the beginning of this lecture. I said we have to distinguish between the way by how we use the term work now, because outside of a physics class in everyday language, we kind of use that a little bit loosely. If you went up to a big bodybuilder and told him he wasn't working hard enough when he's got like 200-pound dumbbells in his hands walking across the gym, that might not be a conversation you want to have with a bodybuilder like that, right? Because clearly he would say that, or she would say that they're doing a lot of work. Well, burning calories is not the same thing as mechanical work. That's the point I'm trying to make here. they are doing they can walk all the way around from here to the beach. And as long as they don't move those dumbbells in the direction of motion, they are doing zero mechanical work, even though they're clearly burning a lot of calories, right? And so, yeah, so that's the big distinction. Mechanical work is a very specific definition defined by the dot product. And I wrote it earlier. A component of the force must be in the same direction of motion or parallel along the same coordinate direction. If it isn't, it doesn't matter how difficult it is or how many calories you burn in this example, you're doing zero mechanical work. Okay? Everybody understand that? Give me some feedback. Yes, okay, good. Wonderful. Now, who had part 3? Sure, I thought you had part 3. Why'd you do part 2? Okay, so whoever had part 2 now
part 2.
do. Yeah, part. So now, sorry. So now you'll do part 2, part 3. You do Dami's what I initially sounded Dami. So tell me. Definition is this, and we can do the magnitude, right? So F delta X cos theta. So you have to go through and evaluate each of those parts. So what is F, Dami?
F is mg.
Yes, because I'm going at a constant speed. That's right. Delta X is just
Delta X.
Delta X, good. And what is the angle between these things now?
0.
Between F and delta? No. What is the definition?
180. 180.
Yeah, who said that?
Down.
Yeah, it's 180. Because F is up, but I'm moving down. So the direction is 180. So what is the amount of work done in step 3?
It's negative of mg.
Negative mgx. Yeah.
mg delta x, yeah.
Delta x, yeah. Because remember, mg is a force, it's not work, and it has units of newtons. But mg delta x is work, and it has units of joules. Wonderful, wonderful, wonderful. So in path 3, I do positive work. I'm putting energy in the system, and as it turns out, it would be energy of position. I'll be giving a potential energy by doing that. We'll talk about that later. But yeah, it's now. Then I walk along path 3. I do no work, and then in path 3, I'm taking that energy, that work. I'm doing negative work on the object. So, what would be the total work that I do between all 3 paths?
Professor, why is it negative for work 3? Is it because you're putting it down?
Oh no, it's cosine of 180.
That's right. What Dami said. It's cosine of 180. The force is up and the direction of motion is down, so the angle between them is 180.
Okay.
See that?
Yeah, got it.
Yes, right. If you need to write that, I wrote it already for you, but you probably didn't understand what it meant. You need to write it, whatever you need to put in your notes to make sure you understand that, then do it. Theta is the direction between the angle between the direction of motion and the direction that the force is applied. Okay?
So cosine 180 is -1, correct?
That's right. And that's why this is a negative mg delta x.
Okay.
Okay. So what is the total work done through this whole thing? Anybody?
0.
0.
0. That's right. Total work done by me in an ideal case is 0. Now, that's not really true, and we'll talk about that probably either next week or later. Because I'm actually, when I hold it, there's friction, because friction is force of contact. So I'm actually burning some energy. Like I'm turning some of the mechanical energy into heat, and I'm actually using more than is necessary to pick it up. Technically speaking, the force of gravity is doing like 0, but like In fact, let's go back and look at that. As a thought experiment, I would like for you to go back and now, because I think someone had said that earlier, I guess Abdul started doing that earlier. So now that we've gone through this thing once, go back and look at the force of gravity through each position, through each trial, and calculate the force of gravity, the work that gravity is doing. You're going to see that every place it's opposite what I was doing. Here, gravity is doing negative mg. Here it's doing 0. Here it's doing positive mg. So gravity is still doing 0 work, even as I'm doing over the whole round, over everything, right? But technically speaking, I'm not really doing 0 because I'm losing a little about an energy because I have to hold on to the thing to pick it up. Some of that energy is being turned into heat and dissipating into the atmosphere. Gravity, on the other hand, truly is doing 0 work. Why? Because gravity doesn't have to, the Earth, which is the source of the gravitational force, doesn't have to touch this object to do work on it. And that leads to something called a conservative and non-conservative forces, which we'll talk about later. But just as a thought experiment, go ahead and, and just think back through mg in the way we did here, and maybe even write it out like this so it reinforces in your mind so you can see. So technically speaking, if I pick this thing up at a constant speed, and that's what I'll go back to you, Abdul, technically the total work done through each point is 0. Because I did positive work mg delta x while I picked it up, but gravity did negative mg delta x. So the total work done on the object was actually 0 by all forces. But that's a different, difference. But yeah, now that we understand that, we could think of it. We could do that. Yeah. So that's an official introduction of the concept of work.
Professor?
Yes.
I have a question. I kind of ask this question when we're talking about drag and terminal velocity. But if the force applied, which is used to carry the dumbbell is equal to the weight of the dumbbell, what keeps the dumbbell in that constant motion? Is it the inertia?
Yes. Yes, it's the first law. That brings you back to some implication of the first law. That's right. The first law says that, it's very good. The first law says that an object will stay at rest or in motion unless acted upon by a net external force. Now, it's true, as you all pointed out, in some very small, shorter time, I do have to accelerate it to get it going to some, to start it to move. But, we're assuming that's like milliseconds or something for me to start it move. But once I start it moving, it's moving, and the forces on it are constant. The forces on it are not changing. There's a applied force up and the weight down. And those forces are equal and opposite, but the object still moves. Why? Because it has motion, and during the process where the forces are equal, the net external force on the object is 0. So the object will continue in motion until at some later point, a net external force is applied to the object. And that point does happen whenever I start to decrease, because you do it really fast and intuitive, so you don't think about it. I decrease the amount of force on the object for a short amount of time till it slows to 0. So during that short few milliseconds, it's decelerating, and the gravity, the force of gravity, is larger than my applied force until it stops. But then when it stops and I'm just holding it there, I'm now back to the first law, where I increase the value of my force to equal mg, but it's not moving. So it will stay not moving until I then change the amount of force I'm applying to it. So it's basically an application of the first and second law. the first law doing the larger amount of times, and the second law doing the infinitesimally small times when I change the force to pick it up or set it down. Does that make sense, Tommy?
Yeah.
Let me give you another problem to kind of drive this home a little bit. Let's go with a, again, I like pointing out these problems with kind of, we're going to use the symbols here. I think it takes a little bit of effort. I know we had a conversation about that theater early on, but you know, it's if you can get it, I think you got this example I gave, but this gives a really, I think, can pay off in the long run in terms of the insight and the learning curve. So I'm going to give another one like that, but let's put the mass on a ramp, sliding down a ramp. And also look for homework problems. I'm going to go ahead and assign homework problems from this chapter today. So you'll have them. You can start working on them over the weekend. We have that up and running. So let's do a frictionless surface first, okay? So we got a mass, M. That's what we know, theta. We know M. So what's given is the mass and theta. And probably we could give the height. Let's say that it's at the top of the ramp and the height of the ramp is D. We probably need that. Let's make it H. And let's say that this guy was at the very top. That may come in handy. So we'll give it frictionless. So mu is equal to 0, frictionless surface. And we know it's going to slide down. So what I want you to do is I want you to determine the work of all forces on the object. Now, right now, it's just two forces. It's just gravity. Yeah, I should have set this up so I could come back. My bad. I didn't manage that break well. But let me help you along. So we got two forces. We've got the weight, which is md. Mg is straight down, right? So mg. And we have the normal force. The normal force is perpendicular to the plane and therefore perpendicular to the direction of motion. So right now, go ahead and calculate the calculate the work done by friction and by the normal force and by the weight. Calculate the work done. Again, work. We'll go with the dot product. In general, is F dot delta X. Delta X being the path. And do that for each one. I'm going to move you along a little bit because I want to try to get a certain place before we leave. We're kind of running out of time. So let's do the normal force. Abdul, what is the angle between the normal force and the direction of motion? Actually, yeah. Good. So work done by normal force, we got to do normal force times delta X times cosine of the angle. Now, actually, you know what? I don't want you to be confused. Let's call this angle, I'm just going to use a different symbol right now. Let's use alpha for this symbol. All right, so we're not confused. Where theta, we're going to use as the angle between, for the work equation. To call that alpha, and so cosine theta, where theta is the angle between n and delta x. What is the angle between the normal force and the direction of motion? Abdul. Okay, maybe Abdul walked away. David Edwards, can you give me the direction, the angle between the normal force and the direction of motion as this object moves down the plane? And in this case, it will be accelerating, actually. Okay, maybe he's not there. David Mwabo. You there? I haven't called on you. Yeah, the angle. So give me the angle.
The angle of what? Of the
Between
normal?
the normal force and the, yeah.
Does it look like?
What's that?
Does it look like 90 degrees?
Wonderful, good job, 90 degrees. So what work does the normal force do as it moves down the plane? David? David? You there?
Yeah.
Yeah, so what is the work done by the normal force then? You're right, it is 90 degrees, so.
Work done by a normal force.
Yeah, Didier, can you tell him and tell him why? Or can you just answer?
It'd be 0 because cosine 90 is 0.
Yeah, thought you'd be able to get that. Yeah, yeah, right. Cosine of 90 is 0, so the work is 0. You see that, David?
Oh,
See
yeah,
that?
yeah. I didn't even know it was cosine of 90. Oh.
Well, I thought that's what you just said. Oh, what? I thought you just said it was 90.
Yeah, now I see.
Okay, all right. So that's 0. Now, look at the weight. Remember, we have to find the component of the weight. There's a couple ways we could do this, right? You could find the component, or you could just take the total weight. Either way, it's going to give you the same answer, right? Look, a couple ways we could do this. So, the normal for the weight is at some angle relative to the direction that it's moving. Now, one simple way to get this is to find the component of mg that is along that direction, because we already know only the component of a force in the direction of motion contributes to the motion. So if this is alpha, if this is alpha here, then we know that alpha is also this angle right here. Let me make it green so you can see it better. That's alpha, and this is also alpha right there. So in terms of alpha, we have mg sine alpha here. Right? And here we have mg cosine alpha. We did all this a few weeks ago, right? So mg cosine alpha is this one. By the way, just as a quickie, Didier, how much work does mg cosine alpha do as the object moves down the plane, and why?
Sorry, Professor, can you repeat that?
How much work does mg cosine alpha do on the mass as the mass slides down the plane, and why? What is the angle of mg cosine theta cosine alpha relative to the motion?
Yeah, 0, wouldn't it? This is my homie. He lives in front of pointing down.
So what's 0, the angle or the work?
It'd be the work.
Yeah, the work is 0 because? That's right. The answer is 0, the angle, but why? Why is the work 0?
Because it's 90.
Yeah, because the object is pointing, well, you said down, but let's say along the along the negative x-axis, which means that it's 90 degrees relative to the direction of motion. So if I compute that, and so that's what I'm pointing out. This angle alpha is not, it would be, if we actually worked it out, we would write it like this. So you might write something like this, the work done by the, I don't know, I guess it's the y component of the weight. So work done by mg y, maybe, I don't know, is equal to basically mg cosine alpha, which is the force, times delta x, which is the length down the plane, whatever that is. We haven't talked about that yet, times the cosine of 90. So they're not the same angles. That's why I didn't want to confuse it, right? The angle, this angle in the equation is the angle between that force and the direction of motion. That doesn't have anything to do with this angle. So this component, mg cosine theta, that is its magnitude. The cosine theta is associated with the magnitude in the vertical or in the y direction. But again, cosine of 90 is 0, so this component, mathematically, you can see that it doesn't contribute to work, but you wouldn't even really have to do that if you understood that it's perpendicular to the motion, right? So the only part of the weight that contributes to the work is this guy, because it's in the direction of motion. Okay, so let's compute that one now. So you might say it like, what is the work done by the x component of the weight? I don't want to confuse this with weight and, because we're kind of mixing symbols there. W I'm using now for work, and I don't want to put W sub W. So I'm just going to put mg x, meaning it's the component of the weight down the plane. So now that's going to be the force. And the force here is mg sine alpha. Okay, so mg sine alpha times delta x times the cosine of 0. Because delta x is, now I haven't actually shown delta x. Delta x would really be some distance like this, right? It would be the path that is moving down the plane. So that's really delta x, something that looks like this, right? And cosine, and so we're moving along delta x, mg sine theta is on that same direction. So this goes to 1. And now we're at the work. Basically, it's the total work, of the thing is mg, right? Is equal to mg sine alpha times delta x. Okay. Now check this out, folks. I haven't really given you delta x. That wasn't one of the given quantities. The given quantities were, I've erased them, but m, h, and alpha. That's all. So technically, this delta x is an unknown. But if I have alpha in h, I could figure out what delta x is. What is delta x? If you think about the right triangle, remember delta x is basically the plane of the incline, and h is the height of the incline, and alpha is the angle of the right triangle that kind of maps them out along with the horizontal direction. So what is delta x in terms of h and alpha?
Wouldn't you be able to use the Pythagorean theorem?
We could use the Pythagorean theorem, but we don't know this distance here. We only know h. So a better thing to use would be the trigonometric identities. Wonderful. Yes, right? We have a right triangle, an alpha. This is x, and that's h. So sine theta is equal to, or sine alpha, excuse me, is equal to opposite over hypotenuse. So opposite h over x, delta x, I guess. So delta x equals h divided by sine alpha. Now, if we substitute equation 9 into equation 7, this is what we have. That the weight, or the work, excuse me, done by gravity, that's the only thing that's actually doing work, is equal to mg sine alpha times h divided by sine alpha. Look at that. The h goes out, the mg sine alpha goes out, and I am left with mgh. That the total work done equals mgh. Now that should look a little familiar if you had physics before. You kind of, it's forecasting what's coming in the next chapter. But it says that up top we have something called, we'll see next chapter, that's called potential energy. All right, the MGH. Got 5 minutes left.
Professor.
Yes.
Is your number 5, is that a WMG and then Y, or is it an X?
It's a Y. It's a Y.
Okay.
That was looking at the work done by the Y component, because the Y component of the force is mg cosine theta, and that is equal to 0. Let me call that 5A and then 5B.
Okay.
Y mg sub Y is equal to 0. That's what we're saying, that the Y component does no work, but the X component actually does all of the work on the object as it moves down, and that work is equal to the mass of the object times acceleration and gravity times the height that the object is above the ground. That's a significant result that we'll talk about next chapter in terms of potential energy. Let me show you something else. This is also a forecaster. I'm going to introduce something real quick that I want you to work on. It's something called the work energy theorem. Now, I don't know if your book calls it that. I think they just say the relationship between work and kinetic energy. But let me derive something really quickly. Let's say that I have a car on a road, and then you go here. And that car, let's use kinematic properties to do it. Let's say that we apply the engine, the force of the engine to the car, and that force is F applied. And it's like you at a stoplight, and you accelerate through a distance delta x, okay? And let's say that our initial velocity v naught was equal to 0. So we're at a stoplight. We press the car, the gas. The engine does work on the object by accelerating it through a distance delta x. So the issue here is I can develop a relationship between the change in the motion of the object and the work done by the car. That's actually something called, this is called the work energy theorem. It relates mechanical work to a change in internal energy. Work energy theorem. And we can develop it with mechanical principles. So let's, we start by, well, we know that, let's apply the equation of motion. We know that if we have a velocity here, v initial, right? And over here, this is, when it gets over here, it's going to have a final velocity, v final. We know that from mechanics, right? And I mean, this doesn't even have to be 0. It just can be whatever initial velocity it was, but let's assume it's, it could be 0. So we know there's an equation of motion that defines this type of situation. Is that the final velocity squared equals the initial velocity squared plus 2 times the acceleration of the car times delta x. That's just from back from kinematics. Now let's manipulate this a little bit. I'm going to take the initial velocity over, so I'm going to have v final squared minus v initial squared equals 2a delta x. Then I'm going to divide by 2 and distribute that through each term. So 1/2 v final squared minus 1/2 v initial squared equals a times delta x. It's just dividing by 2. Now I'm going to use Newton's law. I've got a force on this thing. The net force on the object equals mass times acceleration. That net force is the force applied. So force applied equals mass times acceleration. Let me divide by the mass. If I divide by the mass, I have that the force applied divided by the mass equals the acceleration. Let me take equation 6 and plug it into equation 3. Over here. I'll call this 7. So I have v final squared minus v initial squared equals 2 times, well, 2 is not there anymore. So the A is going to be F, just in term F applied, times delta x over the mass. Now I'm going to multiply the mass through each term. Oh, and I forgot there's a 1/2 here and a 1/2 there. I'm running out of space. Let me come over here and get some better space. And it might be hard to see that. So let me rewrite equation 7. 1/2 v final squared minus 1/2 v initial squared equals F applied times delta x divided by mass. Now I'm going to multiply the mass through and distribute that. So 1/2 mass times velocity squared minus 1/2 mass times the initial velocity squared equals F applied times delta x. So last question of the day. Let's go back to Jesus. What is this quantity right here? What concept that we just talked about that define that what is a force times a displacement times a path? What units will that have, and what quantities does that represent?
Professor, can you repeat the question, please?
What is this quantity on the right? Force times delta x.
Is that what we're doing right now?
You tell me. That's the question. What are we doing right now? What do we call it? Who said that? Dami, yes. Dami answered for you. It's work. Work is equal to force times path. Yes. So what it's telling you is that the work done by your engine as you accelerate through a distance is equal to this quantity on the left. So let me complete this out. 1/2 m v final squared minus 1/2 m v initial squared is equal to work. But does anyone, I'll go with you, Dami, this quantity on the left is actually called something. 1/2 mv squared. What is that?
Kinetic energy.
That's right. It's energy of motion. If you go through and do the units for this, it's going to have the same units as work. it'll be kilograms meters squared per second squared, right? In fact, you can see it here, kilograms, and this is square the velocity, and velocity is meters per second, so it's kilograms meters squared per second squared. That has units of energy, of work, joules. Well, so basically it's showing you that work and energy are actually the same thing. They're the same physical quantity, but we just call them different things depending on what the energy is, how it's being utilized by a system. Right. So we can now define, you probably knew that when I heard that before, that 1/2 mv squared equals kinetic energy. But this derivation that I just gave you, this is where it comes from. Here we define kinetic energy, energy of motion, kinetic energy. And you can use different symbols. People use K or KE. I'm just going to use K just to be simple. K is defined as 1/2 mv squared. So that gives us a definition of kinetic energy. But the work energy theorem relates work to not kinetic energy, but rather a change in kinetic energy. So if we then take this definition for kinetic energy and substitute it back into equation 9, what we have is that K final minus K initial equals the work done in a system, or a more succinct way of writing it is that the work done on a system is equal to the change in the kinetic energy of that system, or rather, work equals change in kinetic energy. And this, folks, is the work energy theorem. It's usually written with a parentheses like that. I'm sorry, a hyphen. Or usually it's written abbreviated, work dash E theorem. Work energy theorem. So it's a way of using work to figure out stuff like the velocity of an object, the final velocity of an object, as opposed to going strictly with Newton's laws. Now, what I want you to do is to take the work energy theorem, what we just did, and apply it to this problem here. Assuming that the mass is at the top of the, started from 0, what is the velocity that it will have at the bottom of this ramp if we apply the work energy theorem to it? See if you can work that out. And you can read in the chapter. The chapter talks about this as well. But see if you can work that out. And we'll start here on next Monday with the work energy theorem, and then proceed with the rest of the chapter. But it's a way of, it's kind of a precursor to conservation of energy, which I know you've heard of. It's a way of doing conservation of energy essentially without actually doing it formally with knowing what potential energy is. But we had to, we've now defined one type of mechanical energy, which is kinetic energy. The other type is this energy of motion. Potential energy is energy of position. But this starts that process. Let's go ahead and work on this, try to do that problem, and then also start to basically finish reading the chapter, and then start working on the homework problems that I'm going to assign from that chapter. I'll do it sometime today, and you'll see it pop up in your module. Sorry, I kept you over a few minutes, but you got some good work done today. This is, we're kind of getting into more, this is, probably a bit more esoteric concept. I mean, we're understanding what energy is and work and stuff. Well, as you can see today, it's not necessarily trivial, but it's not impossible either. You just have to kind of start with a good basis and defining what work is and understanding some of the subtleties of how it behaves is the starting point. So I think this was a good day. I think you guys, I don't think there's any, I just noticed that. there's no females in the class. Yes, David.
What is the main difference between the work energy and the work, which is force times distance?
The main difference between kinetic energy and the work, or the work energy and the work?
Work energy and work itself. Like,
Oh, okay, good. Yes, work is defined as, in the way that I told you, it's force times distance. Work energy is a theoretical way of thinking about work. You can think of work as a force applied to an object, which will move that object to a certain distance. But there's a consequence of that motion. It is that it's going to change the velocity of the object. Do you see that from this starting point? Anytime you apply a force on something, if it's a net external force, it's going to give it an acceleration, which means the velocity is going to change. You understand?
Yeah.
Okay. What we're doing over here is we're using the velocity to define. We're saying that the velocity changes because the internal energy of the system changes. And there's a specific kind of internal energy that we can talk about, and that's energy of motion. So the work energy theorem is not work. Work is a separate quantity. What the work energy theorem does is relate that work to the change in internal energy of the object, specifically the change in energy of motion of the object. In other words, we could go one step further up here. This is not a definition of work. Work is defined independently. But if we use the definition of work, we could write this a different way. We can say that F dot delta X equals the change in kinetic energy of the object. So that should actually clarify what you're trying to ask. Work is not kinetic energy. Work is a change in a force time. Work is a force times, a path. But you can relate the force times the path to the change in energy of motion of the system that force is applied to.
Oh, okay. Okay, I see. It's kind of a pathway.
Yes. Yeah. It's kind of like getting to velocity from a back way, a different way than just applying force directly and thinking about the acceleration. We can think about so like from the second law, like basically work and energy, it's a different theorem than Newton's laws. It's basically a different perspective of thinking about what force can do. Force can accelerate an object and have all the equations of motion, but force can also give energy to a system. So the work energy and kinetic energy, all of that's looking at force from basically a completely different perspective. They're not actually related at all. The concept of work and energy and the concept of Newton's laws. They're not really directly related. They're completely separate theories, but they can give the same answers for quantities like the change in velocity of an object. Does that make sense?
Yeah.
Okay. All right. Read the chapter. That'll help you to go ahead and read through the chapter. You got to start now. All right. Anything else?
No, that'd be all. Thanks a lot, Professor.
All right. Thank y'all. You have a good weekend. Be safe. Go out and vote. Vote if you hadn't yet. And you can still register in California. If you're not registered yet, there's no deadline. You can register on the day that you vote. So,
hey, Professor.
All right. Take care.
Professor?
Yeah.
I have a question.
Okay.
So, based on what you said, work is only done when there's motion, right? Because in energy we have potential energy and kinetic energy. Potential energy, which is an object being at rest, and kinetic, which is an object being in motion. My question is work being done by the forces on an object that's at rest?
That's a good question. I think I can say in general that the answer is no, that you're right. That an object has to, mechanical work, that is. There might be other ways that you can think of work or energy change, but mechanical work is only done whenever an object is displaced. That's right.
Okay.
That's right. That's right. Yeah, I would say that. I think that's a fair statement. An object has to be displaced in order for mechanical work to be done. Yes. Anything else?
Oh, no, that's
Yes. Oh,
Okay, Jesus, yes.
yeah, I have two questions. So, let's see. Okay, so I'm kind of I'm not sure if I get it like completely, the example you have on the board.
Okay.
So I get the first three parts, and then okay, so then yeah, so right there after that step, I'm kind of confused.
Okay, I just jumped to Newton's second law. The step 4 is just Newton's second law.
Okay.
Right, I'm just saying that if I have a car and the example I gave is that you're at a stoplight and you hit the accelerator. Well, you've got an external force. It's the force of the engine on the axle. I mean, I know it's a car and it's all one, but the axle is sitting right. Yeah. So you have an external force that is causing, that is a net external force, net non-zero external force. So it's Newton's second law. It accelerates.
Yeah.
Okay. So that's all I'm saying. Newton's law applies to this. And if I solve Newton's second law for the acceleration, I just have, the acceleration is equal to the net force divided by the mass of the object.
Okay.
So I just took that and substituted into the equation of motion. I substituted F over M into A. That's all.
Okay, that's where I got confused. Yeah.
Because I kind of bunched it up over here, but I rewrote it right here. And it's just, that's all that, this is the change in 1/2 MV, that left side is still this thing right here, but A is equal to F over M, and the delta X is still there.
Okay. Makes more sense.
Yeah, that's all. Yeah. And then after that was just algebra to get to the other form.
And then just one more question.
Yeah.
This problem was from which one? I think it was like the last problem before the one we're doing right now.
Yeah. Okay.
Or two problems before.
Okay.
So I have the work of N is equal to the natural force times the
normal
delta
force.
X. Yeah,
normal
force.
Mm-hmm.
And then times cosine of 90.
Yeah.
And then your work is going to be equal to 0. I get that part. And then after that, you have your work of friction is equal to.
No, it wasn't friction. Friction was 0. This was the weight, work of the weight, of the components of the weight.
Yeah. But the next one was, I believe, friction, correct?
No, they're both weight. I just broke the weight up into different components. I looked at the component along the vertical direction of weight, and that's mg cosine theta. You remember that, right? From last weeks ago.
Yeah.
When we were so the weight has a component along the y-axis, and that's mg cosine theta. But the component along the x-axis is mg sine theta.
Okay. But it's because on my notes I have after that one I have another work, and it's it looks like the friction symbol. So I'm not sure if it was the friction you were referring to.
Wait a minute. Are you doing the one like which problem are you doing? The one we were on the ramp here?
It had a what's it called? Let's see. It was the first problem we actually did
Okay, so
when we had yeah.
yeah, okay,
So
yeah. In that case, yeah, I did. You're right.
yeah.
So we first did the normal force, and then I guess we did friction. I think was next. You're right. Yeah.
Yeah.
Right. Okay. Yeah.
So
Right.
so then I get I get that you have to substitute friction for mu of n, correct?
Yeah. Hmm.
Mu of n, and then times delta x,
Yeah.
and then cosine of 180 is -1. But
Right.
then after that step, it's a work of friction is equal to mu and then mg times delta x. So why is the mg in there?
Yeah. Yeah. Because the normal force for that problem is equal to mg. I thought that would because we did a lot of those problems, right? That incorporates stuff that we did before. The normal force is in the vertical direction, but the weight is also in the vertical direction in the opposite direction.
Correct.
Like in the vertical direction, you have the normal force up and mg down. And in that direction, it's Newton's first law that the normal force, because there's no acceleration, there's no motion or acceleration along the vertical direction as the applied force does work and pulls the object along the horizontal direction. So in order to get, just stuff that we had done weeks before.
Because your n is equal to mg, so then you replace your the mg for the n, correct?
That's right. Yeah. Mm-hmm.
Okay, makes sense now.
Yeah. So we've built on the stuff that we've done to the point where I don't necessarily point it out. We've done a lot of those problems.
Okay.
But it's a good question, though, because if you didn't see it, so now you do. And,
yeah. Thank you.
Yeah, good. Okay, anything else? Anybody?
Professor?
Yes.
F subscript app is the applied force, right?
Yeah, APP, I use that term for applied.
Okay.
Anything, David? If you're still there, you got a question?
No.
Did you say yes? You do have a question or no?
I don't.
Okay, cool. Just listen. That's cool. That's fine. It's all good. So good. I thought it was a good class today. This wasn't trivial stuff. This is a kind of a, it's a leap, because we're kind of incorporating all the stuff from the first third of the semester, the acceleration and kinematics and force and stuff. But I thought you all did well today. I thought the fact that you kind of caught on and hung in there is good. Yeah, it's good. But now we kind of kick it in, definitely read the chapter and start working through those problems. I think there were some issues. David, did you work out? Has everybody worked out issues with the Wally site? Did you not? Are you still? Oh yeah, you did have an issue. Is that worked out or not, David?
I did. It's fine. I feel that lab right now, but
okay.
On the other lab, on the do, I didn't know how to figure out how the graph is.
The graph, yeah. Okay, yeah. So what you have to do is you have to go back to the data tables in the lab bench.
I get that part, but I don't know. I get that part how I don't know how to fill it out on the papers.
It's not. Yeah, you have to it's just a graph. I know it might seem a little funky because it's digital, but you're probably going to have to print out the paper and draw the graph on the paper, unless you have some program like PDF that you can write on it or something. I don't know. But it's just, okay, well then you're gonna have, that's the only way. Is so you have this digital thing, this thing like this, right? So then you just have to, if you print it out, you could just scale it, you know, like it's velocity versus time. So whatever your maximum velocity, maybe each of these points is like 2 meters per second or something. I don't know. Like, so 2, 4, 6, 8, 9, and then time, whatever the increments, 1, 2 seconds. It doesn't have to be 1 second. I don't know what the scale is, but whatever the total amount of time it took, you just,
It'll make it.
yeah, okay, whatever, like just 1, 3, 4, 5, whatever the time is. And so you're going to end up having, I think, 5 graphs, right? So you just, and each graph is going to have a different slope, I think, because of the changes you made in the experiment. So the graph is going to look something like that, I think. And it'll be 5 of them, right? Different slopes. So that's what you have to do. Because it's going to be linear, you know, because the graph the equation that you're going by is velocity equals velocity plus a times t. So you're graphing this velocity in time. So you can see it's a linear equation. So you know the data is going to should be linear. I think that's what they want you to point out. But just to show you that the slope of the graph is the acceleration. So as you increase the force or change the mass because of Newton's second law, right? That's what the lab is about, Newton's second law, F equals ma. It's what I just did over here, this equation. You know, in your chart, you could either change the force or you could change the mass. Either way, that's changing the acceleration. So when you plot, you know, look at this. When you plot v, because really it's the change in the velocity, right? It's like divided by time. Well, what is that? That's acceleration. But that's slope, because it's basically t minus t initial, but t initial is 0. So, you know, rise over run is slope. So when you get like, you know, for this graph example, for example, that's, you know, that's delta v over delta t. That's going to give you the acceleration of that, you know, of that curve, and then so on and so forth. This has a different acceleration, different, you know. So that's the point of that graph. And yeah, you just have to print out the paper and graph it, and then you can take a picture and upload it, PDF or whatever, you know, whatever it does. That's what it wants you to do. All right.
Professor.
Yes.
Just one last question about the graphs. The way I'm doing it, well, I'm pretty sure it's correct, but I'm graphing the final velocity and then the t, the seconds. So if I pick a point and the column for the time, say I want to pick 0.14, and then I have to pick for the final velocity, I have to pick the point and the same row, correct?
Yeah.
Okay.
Yeah.
Yeah.
Right, because that's the velocity, the instantaneous velocity it had at that time.
Yeah. Okay, makes sense now. Yeah.
Yeah, it's this equation right here, right? It's v of t equals v naught times right. So, you know, v of t is equal to v naught times t, and so yeah, you definitely have to, for a particular time, it's a specific velocity, and basically the v naught is 0, basically. So yeah, definitely, because it started at rest. So yeah, definitely you have to get the same velocity in that row. That's right.
Okay.